Well, now we're going to do something a little more challenging than powers of x. Let's try something related to the circle, trig.
Let's do our trig functions. So the nicest one for us is the sine function. So we're going to do this same idea of approximating a function by a line, except instead of x to the n, let's do the sine function. And for x0, we're just going to take 0 because it's easier for us. And we want this to be approximately m times x minus 0.
Okay, now we don't know what, before it was x, it was easy. This is a placeholder for something rather complicated. So let's start by drawing a picture of a circle.
So here's a circle. So you have a big unit circle, circle of area 1.
Radius 1.
Radius 1, thank you.
Right, I'm going to fill in the area table.
And then I'm going to show you how you get sine. So you pick an angle. I'll call that x, because we have an x in our formula. So this is angle x. And we measure in something called radians, which means if we go all the way around the circle, it's 2 pi. So this is a little slice of pizza. And then this point here, this is what gives us the cosine and the sine. So I can think of it as the point cos theta.
Cos x.
Oh,
we're using x. And let's see,
cos x,
sine x. Right. And the length, this radius is 1. Really get that fixed in our minds.
Right. So this is length 1. This is length 1 as well.
Great. So, you know, I didn't actually like so much this idea of radians because it's kind of abstract. But I do like the idea of areas.
Okay.
So let's look at areas of a circle. So here's our angle x, and here's our area A of x.
Can I do the easiest one first?
Sure.
So if x is 0, my little pizza slice is shrunk down to nothing. So its area will be?
0.
Good.
Let's do the other easy one.
How about a whole pizza pie?
A whole pizza, right. I like that. So x goes
all the way around.
All the way around. What's the circumference? 2 pi,
2 pi.
And r is 1. So the area at 2 pi is pi because r squared is 1. Pi r squared. So let's do another one.
How about half a pizza?
Half a pizza. So that's half of this, so that'll be pi.
And you'll have half the area, so it'll be pi over 2. So Matt, can you guess if the angle is x, what should the area be, looking at the pattern here?
Well, these are all divided by 2, so this has to be x over 2.
Great. So that's the area of the pizza slice. We take an angle x, this little pizza slice, to the curve here. The area is exactly x over 2.
That's pizza slice. That's what you eat, this one.
Now, if I was with a fussy kid who only likes straight lines, I could draw a little triangle like this. So here's a piece of the pizza. It's a little bit less than that slice of pizza, but what's the area of that?
Well, let's see. The base of this triangle is 1.
Right.
And we want the height, so let's have the height. And the height is this, so that's this height here, that's sine x. So half the base times the height is the area of that triangle.
So that would be sine x times 1 divided by 2.
Yeah.
And we know it's a smaller area because it's less than the whole slice of pizza. So I've got sine x over 2 is less than or equal to x over 2.
Well, it'd be nice to do what I call the sandwich theorem. So we have x over 2 sandwiched between this, because it could be bigger, and less than or equal to something else. So maybe you can draw the something else.
Well, what we can do is draw another triangle. I'll draw a line straight up to here. Now, the x-coordinate is 1. The y-coordinate, well, we can think of similar triangles. It gives you very familiar things. We know there's a sine function, there's a cosine function.
Tangent.
What's the third one?
Because
exactly.
if we divide by cosine, we get 1 and tangent. So that's great. So now, what's the area of that triangle? That's even easier.
I've got a bigger triangle. What's the height here?
It's tangent of x.
Right.
Well,
So It's a bigger area, so it goes on this side, tangent of x, and because it's a triangle, we have to divide by 2.
All right, so a little complicated because I got sine here and tan here. Let's write the tan in terms of sine over cosine.
So let's rewrite this. And you know what? I'm going to get rid of the 2 while I'm at it, because the 2 is not giving us any useful information. And this tangent is sine x divided by cosine of x.
So we got our sandwich here. The angle x is between sine x and sine x divided by cosine x. And cosine x is a little bit less than 1 where we are, because we're near 0. And
That's right.
so that's,
X is going to be close to 0, so the cosine, this guy, will be very close to 1. So this will be approximately sine x.
slightly bigger, right?
Slightly bigger.
Because cosine is slightly less than 1. All right. Now, what do we do? Well, divide by x.
No, I think we're good here. What this is basically telling us, x is squeezed between sine x and something slightly bigger than sine x. So we've got this pretty good approximation that sine x is approximately the same as x.
Oh, that's really good. So we've used the squeeze of some number pinched between two numbers, and that's wonderful. So where do we take it from here?
Well, how do we make this look like this? So we've got a sine x and a sine x.
Right?
Sine 0, what's sine of 0?
0.
So I could rewrite this as sine x minus sine of 0, because that's just 0. This is approximately, well, x is the same thing as x minus 0.
Oh, and
And
m?
that's here. And then what's m?
Well, it has to be 1.
That's right. So m is 1. And what is m telling us about the function?
That's the instantaneous slope of our sine function at x equals to 0.
Or what we always call the derivative.
And that's
So
it.
this is the derivative of sine. So sine of x. If you take its derivative, you get 1. At least
Oh.
at the point x equals 0.
Have we used this before? What's that, just to
That's
remind
my
me?
little tricky little notation. The little prime means I'm going to take the derivative.
Oh, okay. So there you have it. We've now done, using geometry and areas rather than arcs, the idea of the derivative of sine x at x equals 0, and we're still using this wonderful approximation to do it. No
Right down here.
limits.
There we're done. Thanks again, Matt.
Good job.